So there's this one number that's been living rent-free in my head all week, and honestly, it's a little absurd. 1 petabit per second. That's the target a team at MIT is chasing with their new chip work. And if you translate that into something your brain can actually hold on to, we're talking about roughly 1,000 terabits of data flying across a piece of silicon every single second, on a chip thinner than a single strand of your hair. Just let that sit for a second. Now, the headlines are out here calling this a nightmare for NVIDIA. And I'll be real with you. My first reaction was, okay, that's a bit dramatic. But then I actually went digging. The papers, the researchers, the money behind it, all of it. And I came out the other side thinking the headline might actually be underselling what's going on. So that's what we're doing today. I'm going to walk you through what MIT actually built, why it matters, and whether the biggest name in AI should really be losing sleep. And if you're the type who likes understanding this stuff before it explodes across every feed you own, go ahead and hit subscribe right now, because breaking down exactly these moments is the whole point of this channel. Cool, let's get into it. The bottleneck nobody warns you about. Here's the thing most people get completely backwards about AI hardware. We all obsess over the GPU. How many teraflops? How many cores? How much memory is crammed on there? But the quiet secret of modern computing is that the chip itself is usually not the thing slowing you down. It's moving the data between chips that's quietly strangling everything. Picture it like this. You could hire the fastest chef on the planet, but if your waiters can only carry 1 plate at a time, dinner is still going to crawl out of that kitchen. Inside these enormous AI data centers, you've got tens of thousands of GPUs that have to constantly talk to each other. And right now, they mostly do it with electrical signals screaming through copper wiring. Copper is fast, sure, but it runs hot, it drinks power. And here's the cruel part. The more data you try to shove through it, the worse both of those problems get. That is the wall the entire industry is currently face-planting into. Not raw compute, communication. And that wall is exactly what MIT decided to walk up and punch. So what did MIT actually build? The program is called FUTUR-IC. It's been running since 2022, and it's backed by the National Science Foundation. It's led by a researcher named Anu Agarwal, and honestly, her one-line summary of the whole mission is the cleanest way I've heard anyone put it. Use electronics for computation and photonics for communication. Let me translate that. Keep using normal chips to do the actual thinking, but stop using electricity to haul the data around between them. Use light instead. Light running through tiny optical channels can carry an absolutely ludicrous amount of information while sipping a fraction of the power copper needs. Now, this idea itself isn't brand new. Engineers have been drooling over co-packaged optics for years, but there's always been one deeply annoying problem standing in the doorway. Actually connecting a photonics chip to a regular electronic chip has been hard, expensive, and finicky, and the supply chain to do it at scale just wasn't mature, so it stayed stuck in the lab. That specific roadblock is what MIT went after, and in my opinion, that's the smartest possible thing they could have targeted: optical solder bumps and the petabit dream. So here's what they came up with, and I love this because it's such a clean way to frame a messy problem. If you've ever peeked inside a chip package, the electrical connections between chips are made using these tiny dots of metal called solder bumps. They're the little bridges that let electricity hop from one chip to the next. Simple, standardized, absolutely everywhere in the industry. The catch was that nothing like that existed for light. There was no standard little bridge for handing an optical signal from one chip into another, so the MIT team went and invented them. 3 different optical couplers that they're describing as the first real optical version of the solder bump. Optical bumps, basically. One is called the evanescent coupler, another is the graded index coupler, or GRIN, and there's a third that came out of a separate MIT team led by Professor Dwajan. Each one comes with its own trade-offs. The GRIN can handle a wider range of light. The evanescent one is easier to manufacture and can be packed in tighter so you get more connections in the same space. The point is, engineers finally have an actual toolbox to work with instead of a blank space where the toolbox should be. And this is the piece that gets you toward that petabit dream. Once you can cheaply and reliably pipe light between chips, you can start running a staggering number of parallel optical lanes side by side. That's how you leap from the hundreds of terabits per second we can manage today all the way up past 1 full petabit per second. That's not a modest little upgrade. That's roughly an order of magnitude of headroom. And the first author on this work, Drew Wenninger, has already moved on to the National Institute of Standards and Technology, which tells you this isn't some fringe idea. It's flowing straight into the institutions that set the rules for the whole field. The part that should terrify NVIDIA. Alright, let's talk about why the internet keeps dragging NVIDIA into this conversation. NVIDIA's empire right now isn't really just the GPU. It's the entire system. It's the way they lash tens of thousands of GPUs together into one gigantic machine using their networking and interconnect tech. That ability, making a warehouse full of chips behave like a single unified brain, is a massive chunk of their moat. It's a big reason people pay the eye-watering prices they pay. Now here comes a university program essentially saying, hey, we've worked out a cheap manufacturable way to move data with light at speeds that leave the copper era in the dust. And here's the kicker that genuinely made me lean in. They say these devices can be built using existing semiconductor equipment, traditional foundries, traditional packaging houses. No mysterious new $20 billion factory required. If that actually holds up at scale, then the barrier to entry for insanely fast optical interconnect just dropped for basically everybody who isn't NVIDIA. And whenever a moat suddenly gets cheaper for outsiders to cross, the folks sitting comfortably behind it start to sweat. That's just how these things go. And there's a bigger reason this matters, which is honestly the part I care about most. These data centers are on track to swallow close to 10% of the entire world's electricity by 2030. Chip manufacturing already ties to hundreds of megatons of carbon emissions, plus tens of millions of tons of electronic waste every single year. Moving data with light instead of electricity isn't just faster, it's dramatically more energy efficient. So this isn't purely a speed story, it's a sustainability story wearing a speed story's jacket. And I think that combination is what makes it genuinely dangerous to the status quo. Hold on, let me be straight with you. Now, I'd be doing you dirty if I hyped all this up without handing you the honest picture too. So let me tap the brakes for a moment. This is not a finished product. There is no magic MIT chip sitting in a data center right now, quietly humiliating NVIDIA's hardware. What we actually have is a research program with some genuinely clever building blocks and a very ambitious target painted on the wall. That 1 petabit number is the goal they're aiming at, not a benchmark stamped on something you can go order. And turning slick lab devices into mass-produced parts is a long, brutal road that has killed plenty of brilliant ideas before. Here's the other thing people love to skip over. NVIDIA is very much not asleep. They've already announced their own silicon photonics networking switches, moving into co-packaged optics themselves, pushing hundreds of terabits per second at the switch level with big energy savings baked in. So this fantasy where NVIDIA gets blindsided by the concept of light? A little overcooked. They see the exact same wall everyone else sees. The real question was never whether photonics wins. It's who ends up owning the cheap, standardized, boring version of it that everybody else has to build on top of. And that particular race is wide open right now. Where I actually land on this. So here's my honest take, and I'll admit I'm pretty optimistic about this one. The thing that excites me isn't the flashy petabit headline. It's the part that sounds boring, the optical bumps. Because standardization is the thing that turns a cool science project into an actual industry. Solder bumps didn't sound sexy either. And they quietly made almost every electronic device you own possible. If MIT and the people building on top of this work can make optical connections that cheap and that repeatable, you don't just get faster AI, you get faster everything, running on less power, built with tools the industry already owns. That's the kind of quiet breakthrough that tends to matter way more in the long run than the loud shiny ones. And whether or not it ever becomes a literal nightmare for one specific company, the direction of travel could not be clearer to me. The future of computing runs on light, and it's arriving a lot sooner than most people are ready for. If you got something out of this one, do me a solid and tap that like button. It genuinely helps this kind of deep dive find more curious people like you. And if you're somehow still not subscribed, come on now. You made it all the way to the end. Clearly we're vibing. So hit that subscribe button and stick around, because I'm going to keep pulling apart the technology that's quietly reshaping everything long before it hits the mainstream. I'll catch you in the next one.